Hi everyone. As part of the operating systems course assignment, that is OS344 assignment 4, I'm going to make a presentation on the topic memory management with the reference operating system as Linux. So we'll have a rough overview of xv6 memory first, and then we will develop several tasks like developing a paging framework, page replacement schemes, an enhanced processor details viewer, and then a sanity test to check the above features. And finally, we will implement a copy on write fork. Now, talking about the xv6 overview, xv6 memory is managed in 4096 bytes long pages. Each process has its own table that is used to translate virtual to physical address. In xv6, the process virtual address space is 232 bytes long. However, a user space is limited to only 2 GB. You can see a pictorial description of the virtual address space and the physical address space of xv6 in the picture shown in the slide. Now, the first task is paging framework. An important feature lacking in xv6 is the ability to swap out pages to a backend store. That is, at each moment in time, all processes are held within the main memory. In the first subtask, we are going to implement a paging framework for xv6, which can take our pages and store them on disk. In addition, the framework will retrieve pages back to the memory on demand. The framework was implemented in fs.c and as well as in prog.h. Now, moving ahead, let's see how the paging structure is there in Linux, that is the reference OS. It's a fixed size of 4096 bytes for the x86-64 Linux kernel. Every structure is 4096 bytes and contains 512 entries. Linux basically uses a 4 level of paging in x86-64 architecture. I have also given a reference over here in case if anyone wants to get more details over here. It's a hyperlinked text over there. And then talking about the implementation, what are the files modified in xv6 to achieve this implementation? So basically, it's the fs.c file. Let me show that. fs.c file. We have modified fs.c file, and we have added several functions like first one, we have a create swap file. Create swap file basically creates a new swap file for a given process P. And it requires the PID to be mentioned clearly in order to create a swap file. And in case when the P swap file equal to 0, it means that no slot for the file on store. And the next function which we created is read from swap file. Read from swap file basically reads the size bytes into buffer from the file offset index in the given process P swap file. We can see the file read operation over here. And another function is write to swap file. Write to swap file basically writes the size bytes from the buffer to the file offset index in the given process P swap file. And there is also a remove swap file, which basically removes the swap file for a given process P. And this also requires the PID to be mentioned clearly for its proper functioning. So that was how the implementation of the page framework. So that was how the page framework implementation was done. And moving ahead, the second task which we do will be the page replacement schemes. Now, there are several page replacement schemes like LIFO or FIFO, LAP, etc. LIFO is last in, first out, and then second chance FIFO, as well as least accessed page. Let's see how it's implemented in the reference OS, that is Linux. Linux basically uses LRU, least recently used, and this is not strictly true because there are no lists strictly maintained in LRU. LRU basically in Linux, there are two lists, active list and inactive list. Active list contains the working set of all the processes, and inactive list contains the reclaimed candidates. Here also, for more details, I have given a hyperlink in case if someone wants to find more details about the page replacement, then they can move on to find it over here. Now, the definition of LIFO, that is last in, first out, then second chance FIFO, and how can we make it? So how do we select the page replacement policy? That's done by the command selection equal to, say, scfifo. It opens up Kemu with automatically following the given page replacement policy. And you can start working on the game on this way. And the third task is enhanced processor details viewer. So what happens here is that when you type Control P in KMO, it gives a detailed account of the current running process. The Control P commands gives more information than it was earlier in the normal KMO. We have modified it in such a way that it also prints the total number of pages which are currently paged down. Then the total number of allocated pages to each process, the total number of page faults, and the number of times in which the pages were paged out. Okay, now implementation. Here we have created a sanity test to implement it, and the sanity test is done in mymem.test.c. So here we have this sanity test, which we have a global test, which basically gives us the total number of pages which are currently at present. Let me show it over the screen now. Okay, now when we type Control P, it gives us details about the two processes which are in sleep, and then we have the detail like 456847 out of 57054 free pages in the system. When we run the mym test sanity test and then type Control P, we can see a new memory allocation over here, mym test, and here we can see that the 6764 out of 57054, which means that a few pages have been allocated for this mym test, because of which there was a decrease in the total number of pages. This best shows the page allocation technique in KMO. And the next task is copy on write task. Copy on write is sometimes referred to as implicit sharing or shadowing. It's a resource management technique used in computer programming to efficiently implement a duplicate or copy operation on modifiable resource. So what it basically means is that suppose you fork a process, you create a child process for a parent process, and suppose if they are using the same resources without any modification, then we do not have multiple copies of the same resource. Instead, we can have just one copy and it can be shared between the parent and the child. And this is what exactly copy on write mechanism says. It maintains a single copy of the resources until any of them tries to modify it. In this way, we can have an efficient use of the memory. Now, does the reference OS Linux use COW? Yes, definitely. The copy on write pages are also used in Linux kernels. Same page merging, but these features are missing in xv6. So let's see how to implement those features in xv6. The main modification is done in the file kellogg.c. Let's have a look on kellogg.c. Yeah, have created several functions like the get reference basically gets the count of the number of pages, number of processes which are currently using it, like basically get reference count, and then decrease the reference count function which decreases the reference count. Then to get the number of free pages, we have another function to get the number of free pages at any time. Increment reference count, another function to increment the reference count. And then yeah, we have the normal Kellogg function over here. Yeah. Inside vm.c, we have a copy vum function which calls several other functions like increment, reference e, map pages, etc. Now the implementation part. For the implementation, we have created several test cases. So the first test case, yeah, we have created several test cases for the implementation part. Inside vm.c, we first calculate the initial number of free pages before the child modifies any of the data which the parent used. Okay. Now, then we also calculate the final pages after the modification. At present, there are no modification. This line has been commented out. Let's see what happens when there is no modification done at all. We make a demo. And we now run the test case. Since there was no change or no modification made by the child process in the parent process's resources, then we didn't have any decrease in the number of free pages allotted because they were using the same common resource. Now, suppose if I try to change any of the data, say I equal to 4, which means that the parent's data has now been changed by the child. In such a case, according to the principle, it should create a new page, which means that the number of free pages decreases. Let's see what happens inside Kemu. Yeah, number of free pages decreases because what happens here? It clearly says what happens because initially the child was not modifying any of the resources which the parent used, because of which it printed error, no decrease in the number of free pages. But in the second case, the child modified I equal to 4 from I equal to 3, because of which there was a change in the initial free pages and the final free pages, as a result of which the number of free pages decreases. This best shows how the copy on write principle is implemented inside the xv6. Yeah. On a quick summary, the tasks which we implemented are page framework, a page replacement schemes, enhanced process details viewer, which basically is the printing of more details using Control P, and finally a copy on write mechanism. I thank everyone for watching this. Thank you.